Wait lang.
Um,
Okay.
Good evening, guys. My name is Anika Shah, and today I'm going to present my research on advanced predictive modeling of immunotherapy efficiency in lung cancer. This work was conducted under the guidance of my mentor, Sarah. In this presentation, I'll walk you through the key aspects of our study, including the background, methods, results, and implications. So let's get started with the key concepts and objectives of our research. So to start, I'd like to highlight the 5 main keywords of our research, which are crucial to understanding our study. The first is advanced predictive modeling, which refers to using statistical techniques to predict outcomes consistently and accurately. Next is immunotherapy, which is a type of cancer treatment that helps the immune system recognize and fight cancer cells. It's usually in the form of medicine as opposed to the traditional treatments like chemotherapy and radiation. And then lung cancer, specifically non-small cell lung cancer, which is the most common type of cancer. And then gene expression profiling, which is a method used to measure the activity of thousands of genes at once to create a global picture of a cellular function. And finally, biomarkers, which are biological molecules found in bodily fluids or tissues that indicate the body's condition. Biomarkers are often used to determine how well the body responds to a particular therapy. So these keywords will guide us through the objectives and findings of our research. So let's begin with some background on lung cancer and immunotherapy. Lung cancer is a major global health issue and the cause of most cancer-related deaths worldwide. As mentioned before, non-small cell lung cancer is the most common form of this disease. Traditional treatments like chemotherapy and radiation have been the solutions, but immunotherapy represents advancement, offering new hope for patients with advanced stages of cancer. So immunotherapy works by boosting the immune system ability to recognize and attack cancer cells. Despite its potential, there's a lot of variability in how patients respond to these therapies. So this inconsistency highlights the need for more effective predictive biomarkers that can better guide treatment decisions. Currently, biomarkers such as PD-L1 and tumor mutation burden are used to predict patient responses to immunotherapy. PD-L1 is a protein expressed on the surface of cancer cells that can suppress the immune system from attacking healthier cells. Tumor mutation burden is the number of mutations in a tumor. So while these checkpoints have shown promise as biomarkers for predicting patient response, they have many limitations, which are mostly inconsistencies. Given these challenges, there's a growing interest in exploring alternative biomarkers. One of these alternatives is gene expression profiling, or analyzing genes in tumor cells to find the ones that are the greatest predictors for response. This method offers a broader perspective of the tumor's molecular state, potentially providing more accurate predictions of response. In our study, we aim to investigate the relationship between specific gene expression patterns and immunotherapy response in patients with lung cancer. Our study had 3 key objectives. The first was to analyze gene expression patterns to uncover how specific genes correlate with responses to immunotherapy. Their second objective was to identify key biomarkers by identifying genes with significant associations to treatment response. We aim to find new biomarkers that could potentially improve prediction accuracy. And finally, our third objective was to develop a predictive model that could classify patients based on their likelihood of responding to immunotherapy. So this would assist in more personalized treatment planning for patients. We used advanced bioinformatics tools to achieve these objectives, including training and testing our model with recent patient data. So these are the methods we employed to carry out this study and achieve our goals. So how did we process and collect our data for use? Our data source was Massachusetts General Hospital, where we analyzed gene expression values from 56 patients with lung cancer. Each patient's response to immunotherapy was categorized as either a 1 for a positive response or a 0 for resistance. To measure the gene expression values, we employed several computational techniques. We measured the gene expression levels in each gene using a digital spatial profiler, and then we collected tissue samples and stained them with a special dye that allowed us to see what type of cells were present in the tissue. Finally, we ran the samples through a final platform which counted the quantities of the genes in the tissue. To illustrate, Figure 1 on the right shows the tissue samples and how they were sectioned into blocks for analysis, while Figure 2 provides a workflow diagram of the process. To analyze the data creator model, we developed a program in RStudio. The data was divided into two sets, one for training and the other for testing our model. Blocks 1, 2, and 4 were included in the training set, while block 3 was used for testing. So this approach helped ensure that our model was well-trained and validated on unseen data, reducing the risk of overfitting. We imported the training dataset as a CSV file and assigned the variables to columns in the dataset. The genes and their corresponding expression levels were extracted as the independent variables, while the dependent variable was set to the response. As shown in Figure 3, this code snippet from our R program illustrates how we imported and split the dataset, setting it up for further analysis. So given the complex nature of our data, we decided to implement elastic net regularization in our model. Regularization is a technique designed to make data simpler by eliminating elements that have no predictive value. So there are two types of regularization, L1 and L2. The elastic net model is a combination of both that requires two parameters, alpha and lambda. So in our program, we used a package in RStudio to explore a range of alpha values from 0 to 1. We used cross-validation to test 1,000 values of lambda and find the one that gave us the smallest cross-validated error. Two of the subsets were used for training, while the third was used for validation. And then using the optimal parameter we found, we developed our elastic net model. The performance of the final model was evaluated using a separate testing dataset to ensure that the predictions were not overly fitted with the training data. We measured the model's accuracy by evaluating the AUC score. The AUC is the two-dimensional area under the ROC curve, which is a visual representation of our model's ability to distinguish between responders and non-responders. So the AUC provides a single value between 0 and 1 that represents our model's ability to make accurate predictions. A higher AUC score signifies better model performance. The figure on the right shows an example ROC curve of our original model before finding the optimal parameters. So as mentioned before, we conducted a grid search to determine the best values for the parameters in our model. We systematically tested alpha values ranging from 0 to 1 in increments of 0.1. We performed threefold cross-validation to identify the best lambda as measured by the AUC score. The ideal parameters were chosen based on the highest AUC score, which ensured that the parameters provided the best performance of the model. So this table depicts the performance of our model across the different range of alpha values. The best alpha was 0 and the best lambda was 2.4. So moving on to feature importance. Feature importance is the measure of the impact of each gene we found on our model's predictions. By identifying the greatest and focus on those with the highest impact for further research. In our analysis, we identified several key genes that significantly affected the model's performance. To visualize this, we created the feature importance plot on the right, showing the relative significance of each gene on our model. In this plot, the genes with the longer bars are those that most strongly correlate with the patient's response to treatment. This analysis not only highlighted the most critical genes, but also guided us in prioritizing which biomarkers to study further. Here we present a table of the top 10 genes identified in our study, along with their coefficients and biological roles. The coefficients represent the importance of each gene in predicting immunotherapy response. The genes with the highest coefficients have the most weight in our model. While our findings show potential as future biomarkers, it's essential to acknowledge the limitations of our study. The small sample size of 56 patients and the fact that the data was collected from a single hospital could introduce many biases. So for broader applicability, future studies should involve multi-center and more diverse patient data. Additionally, further cross-validation is required to ensure that our model is as consistent as possible. In conclusion, our study has identified several key genes associated with immunotherapy response in lung cancer patients. We also created a consistent predictive model that can classify patients based on their likelihood of response. These findings not only enhance our understanding of lung cancer and immunotherapy, but also offer potential biomarkers for predicting treatment efficiency. Moving Further validation and exploration of these genes could lead to more personalized and effective treatment strategies for patients. These are some of the key resources we use. Please feel free to reach out for any extra information. I would also like to extend a special thank you to my mentor for her guidance and support throughout this project. I could not have done it without her, and I'm so grateful to this amazing opportunity from Talaria. Thank you for your time.